Hello, welcome to an introduction to integrals. The presumption is that you've worked on antiderivatives before, and this is going to be very little difference between antiderivatives and integrals. Now, the difference is subtle and important to mathematicians, but to the average workaday math student, it's not going to matter too much. So basically, when I was working with derivatives, we needed to have an operator, like a symbol, like how we have a square root as an operator, which symbolizes square roots. For derivatives, we had an operator that was d dx. So this is the notation that meant take the derivative of some function. So that's where we get dy dx from. Take the derivative of y with respect to x. So just like with any other mathematical operation, if it's important enough, it gets its own symbol. So the symbol for antiderivative, and it's a little bit more complicated than that, but I'm just going to simplify for you, is this little integral sign. It looks like an elongated S, and it's because it is, and the origins for this will become more apparent as we continue. The other thing that makes this different is there's this inexplicable dx attached. Again, there's a totally perfect reason for that, but we're going to work on the notation first, and then we'll try to figure out what this is for and why that looks like an elongated S. For now, though, all you need to know is when you see this elongated S, that's a symbol for antiderivative, and we call it the integral symbol. So that's why you'll oftentimes hear these called integrals, and our job is to integrate, which just, again, feels very much like finding an antiderivative. So for this particular expression, first thing I'm going to do is acknowledge a truth about integrals. Just like derivatives, the integral of a sum is equal to the sum of the integrals. In other words, we can integrate each part of this expression, because it is a sum, separately. Notice I kept the dx with the integral and the dx with the integral, so I've created two separate problems, each to be anti-differentiated. So the first case, the integral x to the 1/2, recall that the objective is to raise the power by 1, so 1/2 becomes 3/2, and then divide by that power. Dividing by 3/2 is multiplying by 2/3. E to the x, thankfully, integrates to be e to the x. The only other thing I do then is I add this thing called plus c. And just to quickly talk about that, there's a constant at the end here, and I don't know what it is. I know that if I were to check my answer, I would check my answer by taking the derivative of this, and the derivative of this, and the derivative of c. But since c is a constant, its derivative is 0. Another way to look at this is there was a function, and when I took its derivative, I got square root of x plus e to the x. Now the problem is I don't know if there was a plus 3 or a plus 5 or a plus square root of 2 or anything. I don't know if there was a constant here, so I add an arbitrary constant to hold its place in case there was one there. Again, we'll talk more about that later, but for now, the expectations from all of you in terms of your notation, when you write a problem, you should always show the integral, then the function, and then you should always put the dx there. If you leave the dx out, you get bumped for notation fouls. After you anti-differentiate each term of an integral, then add a constant. If you don't add that extra constant, you're not acknowledging the truth of the matter there either, so you got to make sure you do that. Put it back in the form where I found it, that is to say, it was in radical form when I found it, so I take my exponential form and put it back into radical form. It's not a big deal. And then to check your answer, you take your answer and put it in as a function. You ask Desmos, or the calculator, to take the derivative of your answer, and then you put in the given function. You have to make sure that the derivative of your answer is equal to the given function, as shown on this graph. So, another quick example then. Starting off, recognizing this is the integral of 3e to the x minus 1 over x dx. I'm going to start off by separating the integral of a difference is equal to the difference of the integrals. Here's another truism with integrals. Constants can be pulled out of the integral and basically gotten out of your way. So instead of the negative 1 over x, I'm going to write minus, taking out the negative 1, and then just have the integral of 1 over x. We know that the antiderivative of e to the x is e to the x, so we're going to have 3 times e to the x, and then we're going to have the antiderivative of 1 over x is natural log absolute value x, and then we add the constant. Notice I integrated twice, but I only added one constant. Since we don't know what the constant is, they're just going to all merge together. So maybe this one had a constant of 2, and this one had a constant of 7, so this would be the constant 9. But since I don't know any of them, I just call it one constant. I don't need to write it twice. And the last thing is I have my answer, the derivative of my answer, and the given function, and my job is to make sure that those match. Notice I used absolute value of x in the natural log. That's the way to make sure I get both wings. Moving on, one last example, and I don't need to talk much about this. It's just another example of the same process. So the reason for the third example is to show you that this generally starts to become pretty algorithmic. You start to get the hang of it, but the goal for today is to practice the antiderivative skills that we've been working on, but to couple that with the new notation of integral. And we're going to use the word integral from now on, and we use the integral symbol instead of antiderivative, and we have the extra dx's to worry about, and we also add that arbitrary constant. So that's just something to practice. We'll talk more about that later. Thanks for watching.